Hey guys, this is Dr. G here, and in this video we are going to talk about chemical quantities and reactions. In other words, we are actually going to use the stoichiometric ratios which we obtain when balancing chemical reactions, and we are going to use those values, those stoichiometric ratios, in order to quantify chemical reactions. An important fact about chemical quantities or chemical reactions is that in a chemical reaction, the mass of reactants is actually the same as the mass of products. So this is an important fact about chemical reactions. The mass of reactants is the same as the mass of products. In this example, I have in this slide, I have a reaction between iron and sulfur, giving you iron 3 sulfide. So uh, if you add the mass of iron that was reacted with the mass of sulfur, it should be equal to the mass of iron 3 sulfide that you generate from this reaction. So this fact is actually known as law of conservation of mass. Okay, so according to this law of conservation of mass, matter cannot be created or destroyed. That is the first thing that we understand from this law. And then of course, there is no change in total mass occurs. Okay, so total mass of reactants should be the same as total mass of products. Therefore, the mass of products is equal to the mass of reactants. So most importantly, the mass of products is going to be equal to the mass of reactants if the reaction has gone to a completion. Okay, the mass of products is equal to the mass of reactants. So keeping that in mind, let's talk about this theory in more detail, or this law in more detail. Okay, I have a reaction between silver and sulfur, generating silver 1 sulfide. Okay, so the balanced chemical reaction is actually given in this slide. And then let's say you are reacting 215.8 grams of silver and 32.1 grams of sulfur, and the reaction will go to a completion if you react these two masses as is. And then you will get silver 1 sulfide, and the mass of silver 1 sulfide will be 247.9. And if you take a look at these numbers once again, the mass of reactants is equal to the mass of products. So basically, according to law of conservation, the mass of products is equal to the mass of reactants. Or in other words, no change in total mass occurs during a complete chemical reaction. All right, so this is basically a recap of what we learned in this chapter. We learned 5 different chemical reaction types. So by now you should be able to put together a small chemical reaction. And also we talked about oxidation and reduction reactions in more detail. Okay, so in this part of the chapter, in chemical quantities, we will use all of these chemical reactions. Okay, all of these chemical reactions. And we learn how to balance all of these chemical reactions. That is the most important thing that we learned. Okay, in this chapter we learned many different ways to balance chemical reactions, and I hope that you guys are experts in balancing chemical reactions by now. So let's consider the following equation. Okay, you have iron reacting with sulfur, giving you iron 3 sulfide. You have iron reacting with sulfur, giving you iron 3 sulfide. So if you balance this reaction correctly, you need 2 in front of iron, you need 3 in front of sulfur, and you don't need anything in front of iron 2 iron 3 sulfide, which means it is number 1, right? It is number 1. So we already know how to balance these equations, but what does this stoichiometric ratio mean? So what does these numbers that we obtain by balancing reactions mean? It basically means how many moles of each reactant and each product is formed during the reaction. So in this simple equation, this 2 in front of iron and 3 in front of sulfur just simply means that if you use 2 moles of iron, okay, you will need 3 moles of sulfur to obtain 1 mole of iron sulfide. That is all uh, all you need from balancing a chemical reaction. So these stoichiometric ratios basically means the molar ratio between each of the reactants and products. Okay, each of the reactants and products. So basically, according to the stoichiometric ratio, the molar ratio between iron and sulfur is 2 to 3, and the molar ratio between sulfur and iron 3 sulfide is actually 3 to 1. Okay, so these stoichiometric ratios are directly proportional to the molar ratio of each of the reactants and products. So this fact is actually very important in doing calculations. So basically, using that information from the balanced chemical equation, using that information from the balanced chemical equation, okay, we can come up with molar ratios, or technically we call them mole factors. Molar ratios, or we call them mole factors. So basically, using these stoichiometric values, we can write mole factors for any two different reactants or products, or between reactants and products. So basically, in here I have given you the mole factor for iron and sulfur, iron and iron 3 sulfide, and sulfur and iron 3 sulfide. So basically, as you can see, you simply have to use the stoichiometric values or ratios in order to obtain these values. Okay, all right, so that is how we use these stoichiometric ratios in order to obtain mole factors. So in the next slide, I think I have a small study check. Okay, small study check. See if you could complete this without my help. You might want to pause the video and see if you could get this answer. Okay. All right, in this study check, I want you to consider the following equation between hydrogen and nitrogen gas. Okay, and it will generate ammonia. Okay, so in this reaction, I have given you the balanced chemical reaction, so you don't have to struggle in balancing it. Of course, I'm pretty sure you can balance this reaction within 30 seconds. But anyway, so if you consider the mole factor between hydrogen and nitrogen, so you are worried about hydrogen and nitrogen. So the mole factor should include the stoichiometric values for hydrogen and nitrogens, right? So for hydrogen, it should include number 3. For nitrogen, it should have number 1. Okay, it should have number 1. So every 3 moles of hydrogen should have 1 mole of nitrogen. Okay, so the correct molar ratio, the correct mole factor is actually number 2, where for every 1 mole you need 3 moles of hydrogen. Okay, so the correct answer is number 2. If you take a look at the second part of this question, a mole factor for ammonia and hydrogen. Okay, so the important mole stoichiometric ratios or coefficients for ammonia and hydrogen are number 2 and number 3 respectively. So the mole factor should include 2 for ammonia and 3 for hydrogen, right? 3 for hydrogen. So the correct answer is once again number 2. All right, so that is how you get it. So if you ever want to get the mole factor between two different reactants or products, or between a reactant and a product, you will simply use the stoichiometric coefficients. Okay, stoichiometric coefficients that you obtained from balancing chemical reactions, and these stoichiometric ratios are directly proportional to the mole ratio between two different components in a chemical reaction. All right, okay, so let's go to the next slide, which is basically calculations with mole factors. This is actually the more important discussion in this presentation. Okay, so in here we are trying to do some calculations with mole factors. Okay, here is a sample calculation. Okay, let's not worry about the answer. Okay, let's take a look at the question that we have in hand. Okay, we have a reaction between iron and oxygen forming iron 3 oxide. Okay, and then we also know that in this reaction, we also know that we have 6 moles of oxygen. 6 moles of oxygen. Okay, so you know how many moles of oxygen you have. You actually have 6 moles of oxygen, and then they want us to calculate how many moles of iron 3 oxide it will generate from this reaction. So this is actually one of the key quantification calculations that we will do in this chapter. So in chemistry, it is very common to know how many reactants that you should use in order to generate a certain amount of products. Or let's say, sometimes, let's say you are working in a chemical factory and your boss will tell you, okay, you need a certain type of products, and then they will tell you what is the quantity of the product that you need. Let's say they will give you a certain amount of time to generate that many amount of product. So if you are working in industry, you don't want to randomly pick certain amounts of reactants or hoping that you will get an approximately the amount of product that your uh, boss want you to get. Okay, instead what you do is you will basically have to calculate how much reactants that you will have to use in order to get the certain amount of product, right? So that is the main objective of these discussions. Okay, we always try to quantify reactants or products based on what we know. Okay, so let's do this calculation in a separate piece of note. Okay, so let me do this same calculation in a separate piece of note. So what I have is a reaction between iron and oxygen. So when you're writing a reaction, you always write it first, okay, with the state. Okay, so iron is a solid, oxygen is a gas, and this reaction will give you Fe2O3 as product, and which is also a solid, a brown color solid. And if you balance this reaction correctly, you will get number 4 in front of iron, and number 2 in front of iron 3 oxide, and then number 3 in front of oxygen. Okay, I hope that you guys can handle balancing reactions now. Okay, so let's see what we know about this. Okay, let's see what we know about this calculation. We already know how much oxygen we have. So they are telling us they have 6 moles of oxygen. They are telling us that they have 6 moles of oxygen. Okay, and they want us to calculate, okay, how many moles of iron oxide. Okay, so they want us to calculate how many moles of iron oxide they can get if you use 6 moles of oxygen. So the assumption is that you're using 6 moles of oxygen, and then you are using more than enough iron. Okay, so iron is not a limiting factor, so we need to calculate how many moles of iron oxide you need. So what you need is moles of Fe2O3. This is what you need to calculate. You will start with what you know. Okay, what you have is 6.0 moles of oxygen. This is what you have. Okay, and then to get to the moles of iron oxide, what you do is you will use a mole factor. You will use a mole factor that involves iron oxide and oxygen. Okay, you will have a mole factor that involves iron oxide and oxygen. So this mole factor should have number 2 and number 3. Okay, so basically the ratio between oxygen and iron oxide is 3 to 2. Okay, so if you have 6 moles of oxygen, you will use a mole factor and multiply 6 moles in such a way to obtain the moles of iron oxide. So in here you will use a mole factor where you will have number 2 on top and number 3 at the bottom. Why do we need to have number 2 on top? Because this number 2 is the coefficient related to what you want to have, which is iron oxide, right? So you are calculating the moles of iron oxide. If you're calculating the moles of iron oxide, you better have number 2 on top. Okay, because that is what you need. And you already know how much oxygen you have. So 3 should be at the bottom. Okay, so you will arrange a mole factor using 3 and 2 should be on the top because you are looking for iron oxide, right? So if you do the calculation correctly, your answer will be 4 moles. Your answer will be 4 moles. 4 moles. Here is your answer. Okay, so X will be 4 moles. Okay, so in here you will get 4.0 moles. And let me, how do you confirm that this answer is correct? Here's the thing. Okay, so the ratio between oxygen and iron 3 oxide is 3 to 2, right? That means 3 moles of oxygen will get you 2 moles of iron 3 oxide. 3 moles of oxygen will give you 2 moles of iron 3 oxide. How do you know that? From the stoichiometric ratio between oxygen and iron oxide. Which means, if you want 6 moles, which is twice as 3, okay, so if you want twice as oxygen, if you use twice as oxygen, you should get twice as iron 2 oxide. So if you use 3 moles, you are getting 2. If you use 6 moles, you are getting 4. That is one way to understand it. Or in other words, the ratio between oxygen and iron 3 oxide is 3 to 2. The ratio between oxygen and iron 3 oxide is 3 to 2, right, guys? 3 to 2. So which one is big? 3 or 2? Of course, 3, right? So you have to use more oxygens as compared to the moles of iron oxide that you get. The moles of oxygen is always higher than the moles of iron oxide you get, iron 3 oxide you get. So if you are using 6 moles, you should get something less than 6, okay? Less than 6, because that is how the mole ratio works. So I hope you understand this question, okay? Understand this question. So of course, in your lecture note, you have a dumbed down method to understand this calculation, okay? So at home, I recommend that if you don't understand what I did in this calculation, you might want to read this method, okay? But let's quickly do this study check. All right, so if you are watching the video, you might want to pause the video and then try the study check by yourself. All right, in this study check, I have already given you the balanced chemical equation for the reaction between iron and oxygen, right? I have already given you the balanced chemical reaction between iron and oxygen. And let's do this calculation, okay? It's very similar to the one that we did before, but I want to use a new piece of paper so that you will understand it better, okay? All right, so let's write what we have here: a balanced chemical equation between iron and oxygen. Okay, this is the equation that we have, and let's look at the data that they have given us. They say that you are using 12 moles of oxygen. Okay, so we know that we are using 12.0 moles of oxygen. Perfect. And what do we need to find? Okay, we need to find out how many moles of iron we need. Okay, so this is what that we want to find. Let's call it X moles. So what is the molar ratio between iron and oxygen? It is 4 to 3. 4 to 3. Okay, this is the ratio. Okay, so every 4 moles of iron will react with 3 moles of oxygen. That is what this means. Okay, every 4 moles of iron will react with 3 moles of oxygen. So if you have 12 moles of oxygen, how many moles of iron you need? 16, right? So you can easily do it mentally, but let's say you can't do it in your head. Let's write an equation that is okay. All right, so let's write an equation. So what we need is moles of iron. Okay, this is what we need. What we have is 12 moles of oxygen. This is what we have, and then we will multiply what we have by a mole ratio that was generated by using the coefficients of iron and oxygen. In this mole ratio, you have to have the coefficient of iron on top. Why? Because that is what you need to find. Okay, so in this mole ratio, you have to have the coefficient of iron on top. Why? Because that is what you want to find. That is what you want to find. Okay, and then at the bottom you will have the coefficient of oxygen, because that is what you already know, right? So if you do the math, the answer will be 16.0 moles of iron. Okay, so x will be 16.0 moles. 16.0 moles. That is how you do it. Okay, so all you need is the mole value of one component. If you know the mole value of one component, then you can easily calculate the moles of other reactants or moles of products that you can expect. Okay, products that you can expect. All you need is a well balanced chemical reaction and the mole factor between two different components of interest. Okay, two different components of interest. So for this calculation, we don't need this number 2. We don't need this number 2. Okay, why? Because this calculation does not involve something about iron 3 oxide. Okay, all right, so that is how you do this calculation. I hope you understand it. Okay, all right, so this is the answer, and this is the stepwise method to do this. I hope that you understand it by now. Okay, all right, so if you want, you can pause the video in certain steps and read it, but I think you got it by now. Okay, so the answer is C. The correct answer is C. All right, here I have a nice little calculation you can try right now. Okay, see if you could pause the video now and then do this calculation. This is a reaction between iron and sulfur generating iron 3 sulfide. Okay, so this is the reaction that we have. All right, so in this reaction, you have 1.42 moles of iron. Okay, you know that you have 1.42 moles of iron. This much you know. Okay, this much you know how many moles of iron you have. Okay, so they want you to calculate how many moles of sulfur. Okay, so the two reactants, or the two things, the components that are of interest is iron and sulfur. Okay, these are the two interesting things in here, and you already know how many moles of iron you have, which is 1.42 moles of iron. You know that, and then you want to figure out how many moles of sulfur you need. Let's call it x moles. Okay, let's call it x moles. Okay, so let's figure this one out. All right, so you want to figure out how many moles of sulfur. This is what you need. To do that, you already know you have 1.42 moles of iron, and you will multiply what you know, which is 1.42 moles of iron, by a mole factor generated using 2 and 3. Why 2 and 3? Because those are the coefficients that are involved in the stoichiometric ratio between iron and sulfur, and we are looking for sulfur, so 3 should be on the top. Okay, the number that is responsible for sulfur should be on top, should be on top, and then the number that is responsible for what we already know should be at the bottom. Okay, should be at the bottom. Okay, so this is what you need, and if you do the calculation correctly, your answer will be 2.13 moles of sulfur. Okay, 2.13 moles of sulfur. Okay, all right, so that is the answer. That is how much sulfur you need. And the stepwise method will be here. Okay, you can pause the video and write it down if you have to, but I think it is a pretty simple calculation at this stage. Okay, all right, I recommend that you guys try study check 7.10 at home. Okay, I recommend that you guys try 7.10 at home. Okay, and let me know if you have any difficulties in doing this calculation. Okay, all right. So up until now, the calculations that we did involved moles. Okay, moles. So we knew one type of mole, and then we need to figure out how many moles of a certain other reactant or a product that we need in moles, right? But in real life, most of the times, uh, calculations have to be converted into grams, mainly because mole is a unit that is used usually by chemistry people, and let's say maybe mostly physics people. Okay, so chemistry and physics people are very fluent in mole calculations, but of course rest of the world is more familiar with units that are used to measure, let's say, mass. Things like grams or ounces or lobes. Those are some of the units that general public is used to, right? So when you do these calculations, most often you have to do these calculations in mass. Okay, because of that, when you are doing these calculations, quantification calculations, you have to convert them into masses. Okay, and also most of the times when you were given certain data, you will be given gram values. Okay, so it is very important to know how to correlate these mole calculations into grams. Okay, into grams. So uh, by now you know how to correlate moles into grams. By now you know how to correlate moles into grams, right? So if you remember the equation that we learned in a previous chapter, if you remember the equation that we learned in a previous chapter, which is basically n equals m over uppercase M. Okay, so this is an equation that we learned in a previous chapter. Okay, so I recommend that you guys uh, remember this equation. Why this equation is so important is because it helps you to convert it helps you to convert moles into grams and grams into moles. Okay, this equation helps you to convert moles into grams and grams into moles. Okay, so here is the equation that we learned: n equals m over m. So if you remember the terms, n is the number of moles. N is the number of moles. Okay, and m is what? It is mass, but it is not mass in anything. Okay, it should be mass in grams. Okay, mass in grams. So what is this uppercase m? What is this uppercase m? Uppercase m is actually the molar mass. Okay, so the uppercase m is actually the molar mass. Okay, so the uppercase m is the molar mass. What is molar mass? Molar mass is actually mass of one mole. Mass of one mole. How do you figure that molar mass out? You can directly read it from a periodic table. Okay, you can directly read it from a periodic table for a given atom. Okay, the molar mass is actually the atomic mass in grams. Okay, so if you take a look at an element in the periodic table, this element has certain numbers associated with it. It has an atomic number, which is basically like an index number. Okay, and also it sometimes has a decimal number. Okay, so this decimal number is actually the atomic mass. We learned it in a previous chapter. Atomic mass is basically average mass of an atom of a certain element, right? So average mass of an atom in a certain element is known as atomic mass. So if you get the gram value that is equal to this atomic mass, that gram value has 1 mole of that particular atom. That gram value has 1 mole of that particular atom. Okay, as an example, if you take a look at carbon, okay, so carbon has atomic mass of 12.0, let's say. Okay, atomic mass of carbon is 12.0. You can directly read it from the periodic table. Okay, and then if you measure 12.0 grams of a piece of carbon, okay, that piece of carbon has 1 mole of carbon atoms. 6.02 times 10 to the power 23 atoms of carbon, or 1 mole of carbon atoms. Okay, so basically this uppercase m is molar mass. Okay, so if you by using molar mass, you can always convert moles into grams or grams into moles using this particular equation. So it is very important that you remember this equation. Okay, it is very important that you remember this equation. So usually what happens is that when we were given a certain calculation, they will most likely give it to us in grams. Okay, so people will give you certain calculations in grams, because let's say in an industry they know how many grams or kilograms of product that they need, okay, in a certain day. Okay, so most of the times the input data will be in grams. Okay, so the input data will be in grams. Okay, and then once they give you the input data, let's say you have a reaction between A and B. Okay, then they will give you the mass of A. Okay, so you will use the molar mass of A. Okay, so what you know is the mass of A. You will use the molar mass of A. Okay, and calculate how many moles of A you have. How do you do that? You will simply divide it by the molar mass of A. Okay, molar mass of A, and you will get what? You will get moles of A. So you will get the moles of A. Okay, so if someone gives you the gram value, you will immediately divide it by the molar mass, and then you will get the moles of A. And then you will use the mole ratio just like we did before, and then you will get the moles of B, of course, okay, by using the mole ratio. But once you have the moles, you have to convert it back to grams so that everyone else can understand it. Of course, you are a chemistry person, uh, the mole values, but I mean, if you want to make sure that everyone else understand this thing, then you have to convert these moles into what? Into grams of B. How do you convert moles of B into grams of B? Moles you multiply moles of B by the molar mass of B. It will give you the mass of B. It will give you the mass of B. Okay, it will give you the mass of B. So these are some of the things that we do in chemistry. Okay, that we do in chemistry. If someone gives us anything in grams, we will convert it into moles, and then we will do molar ratio calculations, and then convert the moles of the other kind that we need to know, and then we will convert it back to grams. Of course, this is like learning to swim on the ground. So let's use the calculation and see if we can do this in real life. Okay, all right. So in the next slide, I have a stepwise method to doing those type of calculations, so you can pause the video and then take a note if you have to. Okay, but I think these are some pretty straight calculations. Okay, so here is an example calculation that we have. Okay, this is a calculation between this is a calculation that is related to a reaction between nitrogen and hydrogen. So let me take a new piece of paper and write down what we need. Okay, so in this calculation we have a reaction between nitrogen and hydrogen. They are both gases. Okay, 1 mole of hydrogen will react with 3 moles of nitrogen will react with 3 moles of hydrogen to give you 2 moles of ammonia. Okay, 2 moles of ammonia. So this is a nice single step reaction. Okay, in here they are telling us that they have 32 grams of nitrogen. Perfect. They have how many grams of nitrogen? They have 32 grams of nitrogen. Okay, 32 grams of nitrogen. They have told us how many nitrogen grams they have. Okay, if you use this many amount of nitrogen, and let's assume that you have plenty of hydrogen available, they are asking us, okay, what is the mass of ammonia you can produce? Okay, they're asking us the mass of ammonia that they can produce. So the two reactants of interest is of course nitrogen and ammonia. So if you take the stoichiometric coefficients, for nitrogen it is 1, for ammonia it is 2. Okay, so every 1 mole of nitrogen will produce 2 moles of ammonia. That much we know. Okay, that much we know. Okay, every 1 mole of nitrogen will produce 2 moles of ammonia. That much we know. But in here they have given us the gram value. They have given us the gram value, right, guys? So let's do this calculation. All right, so first of all, grams means nothing in chemical calculations or mole calculations. So we want to know the moles of nitrogen. Okay, we want to convert grams of nitrogen into moles of nitrogen. Okay, how do you do that? You take the mass of nitrogen and you divide it by molar mass of nitrogen. Okay, molar mass of nitrogen. So mass of nitrogen is what? 32 grams. Okay, what is the molar mass of nitrogen, guys? Molar mass of nitrogen is 48. Nitrogen atomic mass is around 14.0. So you have two nitrogens in here. So 14 plus 14 is 28. Okay, 28 grams per mole. Okay, grams per mole. And here's the thing. Okay, grams to grams will cancel out, and you will have moles as your unit. So you will have 32 divided by 28 moles. This is how many moles of nitrogen you have. Okay, this is how many moles of nitrogen you have. Okay, but we need to know the moles of ammonia. Okay, to do that, you will start with the moles of nitrogen. Okay, this is the moles of nitrogen you have, and then you will multiply it by a mole factor that involves the stoichiometric coefficients for nitrogen and ammonia. In here, number 2 should be on top. For this mole factor, number 2 should be on top. Why? Because that is the coefficient, that is the stoichiometric coefficient for ammonia. So 2 should be on top, 1 should be at the bottom, because that is the coefficient for what? That is the coefficient for nitrogen. So if you forget, you can just mentally write, maybe use a pencil and then write down this is the coefficient for ammonia, because that is what we need to calculate, and then 1 is for nitrogen. Okay, that is for nitrogen. All right, so once you have that, you know the moles of ammonia, which is 32 times 2 divided by 28 moles. Okay, I usually don't use the calculator all the time. I will simply keep all the numbers and then do the calculations in one time in a calculator. So what you have is 64 divided by 28 moles. Okay, this is the moles of ammonia, but they are not asking for the moles, they want the mass of ammonia. So they want us to calculate the mass of ammonia. This is what they want us to calculate. To calculate the mass of ammonia, you already have the number of moles of ammonia. You multiply it by the molar mass of ammonia, which can be calculated by using the formula. Okay, so moles of ammonia is 64 divided by 28. Okay, 64 divided by 28 moles. This is the moles of ammonia, and molar mass of ammonia is how much? It is 17. Nitrogen is 14. Take a look at the periodic table. Atomic mass for nitrogen is 14 and hydrogen is 1. You have 3 hydrogens, right? So 1 times 3 is 3. So 14 plus 3 is 17. Okay, 17 grams per mole. Okay, so moles to moles will cancel out. And your final answer will be in what? In grams. Okay, will be in grams. So if you punch the numbers in your calculator correctly, your answer will be around 39 grams. Okay, so you will have 39 grams of ammonia. 39 grams of ammonia. This is how you do the calculation. All right. Okay, so I think I have the detailed calculation in these next few slides. If you want, you can pause the video and then take a note of that as well. But I'm pretty sure I did the calculation in a very good detailed manner. Okay. All right, so the answer is 39 grams of ammonia. Here is another similar calculation, guys. See if you could do this one now. Okay. All right, so this is a reaction between iron and oxygen generating generating iron 3 oxide. So what you have is 45.8 grams of iron oxide. So, okay, so you have 45.8 grams of iron oxide. Well done. And the other important thing is how many grams of oxygen you need. Okay, so you want to calculate the grams of oxygen you need. Okay, for this calculation you will need a mole ratio, and this mole ratio will be constructed by using 3 and 2. Why? Because they are the coefficients that are responsible for oxygen and iron 3 oxide. Okay, so these are the coefficients of interest. So basically 2 moles of, already that 2 moles of iron 3 oxide will give you 3 moles of oxygen. 2 moles of iron 3 oxide will give you 3 moles of oxygen. That is something that you already know. All right, let's do this calculation, guys. Let's do this calculation. So grams doesn't do us any good. Okay, you want to convert the grams into moles. Okay, so first of all you want to calculate the grams of iron oxides to moles of iron oxide. Okay, you want to calculate moles of iron 3 oxide. And then once you have the moles of iron 3 oxide, you can calculate the moles of oxygen. Once you have the moles of oxygen, you will calculate the grams of oxygen. Okay, that is how you will do this. So let me take a small notepad and then do this calculation with you, but this is the last time that I'm going to do this calculation with you. Okay, all right, let's first write down the equation. So the equation we have is iron and oxygen reaction. Okay, right, and the stoichiometric coefficients of important are going to be 3 and 2, because in this calculation they have given us the grams of iron oxide, which is 45.8 grams, and then you want to calculate the grams of oxygen. Okay, grams of oxygen. So these are the calculations that you need to do. Let's start with the number of moles of iron 3 oxide. Let's start with that. How do you calculate the moles of iron 3 oxide? You will use the mass of iron 3 oxide, and you will divide it by the molar mass of iron 3 oxide. Okay, so mass is 45.8 grams, and the molar mass of iron 3 oxide will have 2 iron atoms and then 3 oxygen atoms. Okay, 3 oxygen atoms. So if you add them all up, the total is going to be around 159.7. Okay, 159.7 grams. Okay, grams, but this is not just grams, it is grams per 1 mole of iron oxide. So grams to grams will cancel out, and your answer will be in moles. But don't do the calculations now. Okay, don't do the calculations now. Keep that information for later calculations. Okay, 45.8 divided by 159.7. Right, so these are the moles of iron oxide. All right, so let's calculate moles of oxygen, because we need to calculate the grams of oxygen, right? So the next calculation should include the calculation of moles of oxygen. All right, so what we have is the moles of iron oxide, so which is 45.8 divided by 159.7 moles. Now you have to multiply it by a mole factor, which was generated by using the coefficients of the stoichiometric ratios of oxygen and iron 3 oxide. So we are calculating oxygen, so the coefficient for oxygen should be on top. Okay, coefficient for oxygen should be on top. Okay, so 3 is for oxygen, and of course at the bottom you have to have the coefficient of iron 3 oxide. Okay, which is actually 2. Okay, are we good? All right. So what we have here is 45.8 times 3 divided by 159.7 times 2 moles. Well done. So this is the moles of oxygen. This is the moles of oxygen, guys. Okay. This is the moles of oxygen. So now we need to calculate the mass of oxygen. What we need is the mass of oxygen, because in the answer they're asking us the mass of oxygen, right? Okay, so how do you do that? To calculate the mass of oxygen, you will take the moles of oxygen and then you will multiply it by the molar mass of oxygen. Okay, so you already know the moles of oxygen, which is 45.8 times 3 divided by 159.7 times 2 multiplied by molar mass of oxygen is 32. Why? Because oxygen is 16.0. Okay, atomic mass for oxygen is 16.0, and you have two atoms in oxygen molecule, so you have to multiply it by 2. So 16 times 2 is 32. Okay, 32.0. So this is moles and this is grams per mole, and I really like to use units because it will basically confirm that my calculations are correct, because moles to moles will cancel out and your final answer will be in grams. And I think for this calculation the correct answer is approximate, I mean the answer that you get is approximately 13.8. Okay, which is answer B in this study check. Okay, in this study check the correct answer is answer B, which is this one, 13.8. all right, so that is how you do this calculation, guys. Okay, so I have given you the stepwise breakdown for the calculations. You can pause the video and write it down if you have to, but I think we did get the exact answer. Okay, all right, so 32 grams of oxygen, that is the correct answer. Here is another calculation, guys. Let's quickly do this. You might want to pause the video and try it by yourself now, because at this level you should be able to do this by yourself. Okay, in this calculation you have a reaction between hydrogen and oxygen giving you water. Okay, and then you already know the mass of water, which is 13.1 grams. 13.1 grams. Okay, and they want you to calculate how many grams of oxygen you need. Okay, so this is the unknown grams. So for this reaction the stoichiometric ratio is important. Every 2 moles of water will give you 1 moles of oxygen. That is the stoichiometric ratio between water and oxygen. So let's do this calculation first. First of all, what you have is the mass of water. Okay, you want to convert mass into moles. Okay, so you want to convert mass into moles of water. How do you do that? You take the mass of water, you divide it by the molar mass of water, which is 18. Hydrogen is 1, so you have 2 hydrogens, that is 2. Oxygen is 16, so 2 plus 16 is 18. Okay, 13.1 grams divided by 18.0 grams per mole. So grams to grams will cancel out and your answer will be in moles. So 13.1 divided by 18.0 moles. So this is the moles of water. Once you have moles of water, okay, you want to calculate the moles of oxygen. Okay, you want to calculate the moles of oxygen because they want us to calculate the grams of oxygen. To do that, you need the moles of oxygen. So to do that, you will take the moles of water and you will multiply it by a mole factor, which was constructed by using the coefficients of the stoichiometric ratio between water and oxygen. You want to figure out oxygen, so the coefficient of oxygen should be on top and then coefficient of water should be at the bottom. Okay, so that is how you do it. So 13.1 divided by 18.0 multiplied by 1/2. Okay, so now we have the moles of oxygen. Let's convert that into mass of oxygen. How do you get the mass of oxygen? You multiply the number of moles of oxygen by the molar mass of oxygen, which is 32. which is 32. So you already have 13.1 divided by 13.0 over 2 moles. This is what you have, and you will multiply it by the molar mass, which is 32.0 grams per mole. Moles to moles will cancel out, and your final answer will be in grams. Okay, your final answer will be in grams. If you do the calculation correctly, the answer will be 11.6 grams. Okay, so that is how you do the calculation. First of all, you will convert the grams of water into moles of water. Then the moles of water will be used to get the moles of oxygen, and then once you have the moles of oxygen, you will calculate the grams of water. That is how you do this. All right, so I have the stepwise method to solve this. If you want, you can pause the video and write it down. Okay, all right, and you will get the final answer of 16.6 grams of oxygen. All right, I recommend that you guys try this final calculation by yourself. Okay, try this final calculation by yourself, and then in this calculation you should get 185 grams as the carbon dioxide mass. Okay, as the carbon dioxide mass. All right, guys, let me know if you have any questions. Okay, you guys have a good one. Take care.